chapter 29 is about a closer look at the test of significance. So we're not learning any new tests. We're just kind of going a little more in depth, and all of what we're doing today applies to all of our different hypothesis tests that we've learned about. So when we're performing a test of significance, you're supposed to summarize your data, say which test you used, say if the test was a one-tailed or two-tailed test. Now by that I mean, was it your left tail, right tail, or both tails, and report the p-value. Now why do we need to report all of that in our journal articles, our reports to our boss? Why can't we just tell them our final conclusion? One of the reasons is that we want to be able to check their results. So maybe they did a one-sided test, but really a two-sided would have been more appropriate. Or maybe they forgot to check to see if they could actually do the test, so maybe they forgot to see if their sample size was large enough. The result, and then we also want to see how significant the results were. So did they have a p-value of 4.5 or 0.3 or 0.0002, etc.? Because smaller p-values give us more evidence against the null hypothesis. And so we don't just want to know that they rejected the null, we want to see how much evidence they had against the null. Also, another reason that you report all the details of your study is so that your work is followable, meaning that we could then replicate it and see if we get similar results. So next topic, we're going to be kind of jumping around between topics quite a bit. So how small of a p-value do you need to reject the null? So our p-value tells us the strength of the evidence against the null hypothesis. Now the 1% and 5% cutoff levels that I've told you are the two most common, those are really just guidelines where a p-value of 4.9% isn't really different from one of 5.1%, and in a perfect world we wouldn't really treat them differently. However, we're not quite perfect, and it seems we kind of have to pick a rule and stick with it or we get really confused. And so we did come up with this cutoff level of 5%, but that was just kind of an arbitrary cutoff of the first person to invent it said 5% sounds like a nice round number, let's use 5%, and we all stick with it. But just keep in mind, there's not really this definite division between probable and improbable results of at 5.1% it's not, the null is still probable, but at 4.9% it's no longer probable. That's not a natural mechanic, that's just us setting up a rule. Now also note that many journals only publish results that are statistically significant, or some even require highly significant results. Highly significant meaning you have a 1% cutoff. And this is actually a bad thing because you lose out on information. So even if your study doesn't give you a significant result, doesn't give you a small p-value, you're still contributing to the body of information out there. And those studies should still be published as well. Okay, now interpreting the p-value, remember our p-value tells us how likely the result is under the null hypothesis, or assuming that the null hypothesis is true. The p-value, keep in mind, it only tells you the strength of the evidence against the null hypothesis. It doesn't tell us about the importance of the result, so how important it really is in the real world, or the strength of a relationship. So say we are telling you that two variables are related, it's not going to tell you how strongly they're related. Or it doesn't tell you about the reliability of the design of an experiment. And this one is very important because your experiment is only as good as the design, the way you actually set up your study. If you set up the study and you have a bad setup, your results don't really mean anything, even if you get a very small p-value. So a few things to decide how important a result is or how strong the relationship is. Think of it as applying to the whole population. Think about real-world consequences. So for example, if increasing exposure to a toxin 100-fold increases cancer rates by only 1%, that's not as important as, say, another study that can cut fatalities by, say, 30%. So just keep in mind, the p-value tells us how sure we are statistically. It doesn't tell us if it's going to be important in the real world. Okay, and also to decide how good an experiment is, make sure you ask questions about how the study was conducted. Now, errors in hypothesis testing. Hypothesis testing deals with chances, so we can never be absolutely sure if our conclusions are correct. Sometimes we accidentally reject a true null hypothesis. And sometimes we fail to reject a false null hypothesis. So these are our errors. Now the point of testing is to help distinguish between real differences and chance variation. So we say, okay, I expected this, but I got this. Is that just due to our natural chance error, or is there a real difference? But big differences, just due to chance error, can happen occasionally. So sometimes when we find a statistically significant result, meaning a small p-value, it might have just been a really big chance error, which happens occasionally. But the good news is, if we have a large sample, we are less likely to make errors in our hypothesis testing. So big samples mean less chance error. And we've seen this as a common theme throughout the class. The bigger your sample size, assuming that you do have a good sample design, means that your results will be more precise and you are less likely to make errors. Now, data snooping. So data snooping involves a couple things. Let's first do doing lots of tests. So if we do a lot of statistical tests, we expect to find some statistically significant, or in other words, small p-values. We expect to find some small p-values just due to chance error. So for example, if we test at our 5% level, have a 5% cutoff, we actually expect 5% of our tests to show up as statistically significant just due to chance, even if all the null hypotheses were true. So once again, if you do 100 tests, we expect to get 5 false positives just by chance, just due to that chance error. That's what the 5% cutoff tells us, is that we're going to mess up 5% of the time. Or we expect to mess up 5% of the time if the null is true. So when we say false positives means that you have small p-values, so you reject the null, but the null is true. And so once again, if you do 100 tests, you'd expect to get 5 false positives, where even if the null is true, you're going to accidentally reject it, just due to your chance error. And if you do 1,000 tests, you'd expect 50 false positives. And so statisticians have realized if you go out and you do lots of tests, you're going to eventually get small p-values just due to chance error, but they don't mean anything. And you have to account for that. And so when you go and do your reports, you have to tell people how many tests you did and not just the ones that were statistically significant. Because there are ways to adjust the p-values to take into account how many tests you've done. Now that's beyond the scope of this class. Just keep in mind you have to tell people how many tests you did. Also, another way of data snooping is what our textbook calls singling out the worst. So if we notice that something unusual has happened, it doesn't make much sense to figure out the chances because rare things happen all the time. So for example, let's say we have a town of 50,000 people and someone notices that the rate of a rare form of cancer is 3.5 times the national average. They perform a statistical test and find a p-value of 0.02%. So we say, okay, we weren't very likely to find such a large form or a large rate of cancer just due to the chance error. So they think there's something going on here, and they find high voltage power lines and conclude that these caused the cancer. So, what was wrong with this? Well, first of all, they were wrong to just assume it was the power lines. Maybe it was something else, but more specifically as far as singling out the worst, you have to keep in mind that if you looked at a lot of towns, just due to chance, you are likely to somewhere find a town with a high rate of cancer. So there could be something wrong with this town, but it could also be bad luck. Okay, and also not related to data snooping, but just as a what was wrong with this. Also, they didn't do a study design to let them say that it is the high voltage causing the cancer. Another thing that falls under data snooping is one-tail versus two-tail tests. Now, with one-tail versus two-tail, again, this means our left tail, right tail, or both tails. So researchers like one-tail tests because they're more likely to get statistically significant results, because the p-values are smaller if you only look at the area in one tail. However, the decision should be made before you look at the data, and if there's any doubt about which direction to go, it should be a two-tailed test. And I've actually seen people say, oh, in advance, I think it should be the left tail, and then their sample data actually ends up being more than they expected, and so that left tail ends up being like 99%, and so they'd actually picked the wrong direction. Sometimes that happens, and so sometimes it's safer to go with the two-tailed test if you're really not sure which direction your relationship should be going. Now, in principle, it doesn't matter whether you make a one-sided or two-sided test as long as you report what you did and you decide ahead of time. Now, data snooping, aka deciding which hypothesis to test after your results have come in, isn't a good thing to do. Investigators need to decide what you want to test and then gather the data. If you realize after looking at the data that you need another alternative hypothesis, it's basically a different tail, you need to run the analysis again on a new independent set of data. The next thing to consider is the result actually important? So this is where we talk about the statistical versus practical significance. So keep in mind that significance is not the same as importance. Okay, so statistical significance means that we are sure, statistically speaking, that there's a real difference and not just chance variation going on. Practical significance means that the difference would actually be important, practically speaking, in the real world, or like would it make an actual difference to you? Now, sample size, if we have a large sample, even tiny differences can show up as statistically significant. And then those tiny differences wouldn't really be important to us. But if you have a small sample, then even an important difference might not show up as statistically significant. And in that case, we'd say that the test lacks power. Power is defined as the ability for the test to actually pick up on real differences. Let's talk a little bit about the design of an experiment. There's two things we want to talk about. Number one, a test of significance doesn't check the design of the study. And number two, a test of significance can tell us whether a difference is real, but not what actually caused the difference. So it's up to the actual investigator to use logic and design good experiments if they actually want to show what causes the differences. In this example, experimenters measure how long it takes for a mouse to get through a maze. The average time is 15 seconds. So that's kind of for like all the mice so far. Now it tells us we take a sample and 20 of the mice are given a shot of a steroid and they are timed again. The average time now is 12 seconds with an SD of 2 seconds. And we want to know, is there evidence that the mice with the steroid are faster? And we can assume that the times are normally distributed. So when I look at this, I see things like my sample size equals 20. My sample average equals 12. And my SD equals 2. It told me that our data looks normal, so that's good. Now, which test would I want to do here? It looks like I just have one sample. It looks like, let's see, do I have a big or small sample size? 20 mice, that would be a small sample size. So we'll use a t-test for our average. And I always like to write what is the question I want to know. So in other words, I'm saying, are they faster? Well, how would that correlate in numbers? So if they were faster, then the average should be less than 15 seconds. So is the average less than 15 seconds? Because that was our old time, so if they're faster, it'd have to be less than that 15. Okay, now is there evidence? That means do a hypothesis test. First step is going to be find your hypotheses. So the null hypothesis would be that the average for all the mice on steroids, the specific steroids, is just 15 seconds. So basically it's the same. Whereas the alternative, what you want to show, will be that the average for all mice on the steroid is what? Well, if they're faster, again, it's going to be less than 15 seconds. I always like writing it out in words. Occasionally on the exam, she might write it with just like symbols. She might just say, is the average less than 15 with a less than sign? But I like words just because it's a little less misinterpretable. It's a lot easier for everyone to understand if we use words. Okay, this is a t-test. Let's do some of our preliminary work. We need to know things like, what was our observed average? Our observed average, the average we saw, was 12 seconds. The expected value for the average, well, if our average really was 15 seconds, we would have expected to get 15. And you need to know the standard error for the average. But there's a couple things to do first here. Because it's the t-test, because we have that small sample, we have to compensate for our small sample size by doing SD+. So it's the square root of our sample size over sample size minus 1. Times the SD of whatever we actually got in our sample. Again, this just compensates for our small sample size because our sample size was less than 25. So this is going to be the square root. My sample size was 20, so we'll do 20 over 20 minus 1, so 20 over 19, times our SD, which was 2, which gives me 2.05. It doesn't change it very much, just a little bit. And you need standard error for your average, which we'll just do that same SD, but in our case we do the SD plus to compensate still, over square root of the sample size. So my SD plus is 2.05 over the square root of my sample size, which again was 20. So I should get 0.46. So that was just all of my preliminary work. Now I can find my test statistic. Which is t. So t is always going to be equal to our observed minus our expected value over our standard error. In our case, we're talking about averages, so you can write little averages on there if you wish. But the formula is just always the same, whether it's a z-test or a t-test. So far, everything we've done has always been observed minus expected value over the standard error. So our observed was 12 minus our expected of 15 over the, that's right. 12 minus 15 over standard error of 0.46. Gives me negative 6.52. That seems like a pretty small t value. That's my test statistic. You can also find degrees of freedom, which is equal to your sample size minus 1, which 20 minus 1 gives me 19. Now coming up here, let's find our p-value. We have to use the t-table. And because this is a less than, we're going to want the left tail. So we're going to have t equals negative 6.52, and we want the area to the left. Now there's one problem here. Our t-table actually gives us areas to the right, and it only shows us one side. It doesn't do anything for negatives. So we'll have to say this is the same as, and we'll have to figure out, well, what if I looked at t equals positive 6.52, and I looked at the area to the right of that, that would be on my table and it should be the same. So pull up the t-table. We have again 19 degrees of freedom. We're looking for 6.52, which is going to be somewhere way off here, which means that my p-value is going to be something less than 0.5%. We can't get more accurate than that just on the table. We'd have to use a calculator to get some more accuracy. So this p-value is less than 0.5%. So a pretty small p-value. I didn't tell you what significance level to use. So I'll go through and add it on your notes. Let's just practice here. We don't practice very often. Let's use a 1% significance level. Okay. So with a 1% significance level, our p-value is less than 1%. So our results are, we can say, highly statistically significant. Now, each textbook has different ways they write these, and so that's why I don't really make you memorize highly statistically significant or just normally statistically significant. But our p-value is less than 1%. That is very small. So that is a small p-value. And I will reject the null hypothesis. And I think that's going to be a very small p-value. So really, we have a lot of evidence. But we have evidence that the average time for all the mice on the steroid is less than 15 seconds. So the steroid is working, making them faster. Let's see, what else do we have here? Is there evidence that the steroid makes a difference in the time that it takes a mouse to complete the maze? So notice these two questions might seem the same, but they're not exactly the same. The first one said, is there evidence that the mice with the steroid are faster? This one says, is there evidence that the steroid is making a difference? Okay, so it might seem like they're the same. So up here, we did say there's evidence that this group of mice was faster, but is it the steroid causing them to be faster? So I'm going to write some notes here as I talk. Is the steroid causing them to be faster? Well, in this case, it could just be a bad experiment design, because when the mice run with the steroid, it's actually their second time through the maze. Because you'll notice if you go back up to the directions, it said everyone has run through the maze and then they're given a shot of steroid and they are timed again. So this was our key thing right here that threw everything off. They're timed again. So when we time them, it's their second time through. So the mice might just be running faster because it's their second time through. They've practiced, they already know how to get through. That's probably why they're getting through faster. So the steroid might be making them faster, but we don't actually really know for sure. Was it the steroid? Was it the practice? There's just no way to tell. So they should probably do this experiment again, but have a control group that runs twice without the steroid so they can compare it. That would probably be a better experiment here.
So here's another example. We actually have two different examples of experiments in which the experimenters got a small p-value and believed that they had evidence that ESP exists. But then they actually found out later that their evidence they thought they had was actually caused by something else instead of ESP. So in the first one, a person who thought he had ESP tried to control which side a die landed on, and he specifically tried to get it to land on the 6. And they did this 720 times. If he had no control over the dice, he should have gotten roughly 1 6, or basically 120 sixes. Instead, he got 143 sixes, and the chance of this happening if the person had no control was only about 1%. So the p-value was 1%. So he said, yes, this is a small p-value, and I have evidence of ESP. But later, they used the same guy for a later experiment, and they told him to try and get 1s, but instead he kept getting 6s, and when he tried to get 2s, he kept getting 6s. And they finally realized that the die was loaded and favored 6s. And so it wasn't actually ESP causing this difference between the observed and expected value. It was a loaded die. So even though it was a small p-value, it wasn't caused by ESP, it was caused by a loaded die. And once again, the experiment, or the hypothesis test, doesn't check that. The investigator has to check to see if the experiment was designed well. Now, TART had a machine that randomly picked one of 4 targets, and subjects tried to guess which target the machine would pick next. Now, the subjects guessed 2006 correctly, but if they had no ESP and were truly guessing randomly, they should have only been correct about 1,875 times. And so this p-value was 0.02. So he had a small p-value, and he told everyone he had evidence of ESP. But what they eventually realized was that the machine wasn't randomly picking the targets. Okay. And so there was a little bit of a pattern going on here, and people were subconsciously picking up on it. And so that's how they were picking the targets more correctly. Now, he actually tried this again a couple years later with a correct machine, and the p-value was big and there was no evidence of ESP. So once again, the math in the test is good, but it doesn't actually check to see if the design of your experiment was good. And so just because you got a small p-value, you need to check and see if the experiment was actually designed well, and whether the experiment was designed in such a way to let you draw the conclusions that you want. The next thing we're going to talk about is populations and samples. So we don't do tests of significance on the whole population. Hypothesis tests are only for samples. The reason why is if you know the population data, there's really no reason to do a hypothesis test. So for example, if you want to know what the population average is, you just look at the population data. You don't need a ZRT test to tell you what the population average is when you have all the population data. Also, one of the reasons that then our math doesn't work, so not only is there no reason to do it, but our math doesn't work because the sizes and types of errors are different in a population than they are in a sample. Also, don't do tests of significance on samples of convenience, because then your results won't be accurate. Instead, make sure you use probability samples. Probability samples just meaning random samples. And there are different kinds of random samples you can do that are all good. The ones we've done in this class have all been simple random samples. Okay, there are other kinds of random samples that are still good. You just need different formulas. Replication. If we conduct a test and think we have found something important, we can replicate the study to convincingly show our result. Now this actually comes into play a lot when you have studies that can't be designed properly. So for example, say smoking studies. Because on smoking studies you can't do a controlled trial because you can't force someone to smoke because it's harmful. But these smoking studies can become convincing when they are replicated and show consistent effects. Or also if the effects respond appropriately to dose. So for example, if higher doses show higher rates of disease, etc. And also confirming them with lab experiments. And so once again, if you can't design the experiment properly, one of the ways that you can convince people is by replicating it and showing that we're getting consistent results every time. Now in conclusion, just keep in mind that the test of significance answer one and only one question. So they answer, how easy is it to explain the difference between the data and what was expected for the null hypothesis on the basis of chance variation alone? Or in other words, I might say, if the null hypothesis is true, how likely is it to get such a big difference between our observed data and the expected value just due to chance error? So that's really what tests of significance tell us. But so keep in mind the hypothesis test doesn't check the design of an experiment. It doesn't tell you if a significant difference is important, and it doesn't tell you what actually causes the difference. And hypothesis tests are useful, but they aren't appropriate for all situations, and they are sometimes overused because people learn about them in their classes and they think, I need to use this test. It sounds big and impressive, but they're not appropriate all the time, and many times you'd be better off just estimating instead, or using estimation techniques like confidence intervals. And sometimes confidence intervals will give you more useful results than hypothesis tests anyways.